Ms. Peterson here. Today we're going to be talking about how ionic compounds form and be able to, based on given two elements, figure out how they're going to bond, what the ratio is going to be, and what we would call it. So let's look at the most basic of ionic compounds, table salt, aka sodium chloride. Basically, we have our sodium ion, okay? Sodium has 11 electrons and 1 valence electron. It is a metal, so it's on the left side of the periodic table. And we have chlorine, okay? Chlorine has 17 electrons and 7 valence electrons, so it is one away from getting its complete outer shell. Sodium needs to lose one and drop down an energy level to get its complete outer shell. Chlorine also has a much higher electronegativity than sodium. Okay, the electronegativity can be thought of as the attractiveness of an atom. Okay, so chlorine's electronegativity or attractive is so much higher than sodium's that it just takes that electron. That electron is more attracted to chlorine's nucleus than it is to its own nucleus. So it gives that electron to chlorine, which leaves sodium with more protons than electrons, with a positive 1 charge, and chlorine with more electrons than protons. It has a negative charge because it gained an electron. Okay, now, based on electrostatic attraction, okay, fancy word meaning opposites attract, those two ions attract each other, and that's what salt is. Salt is that sodium ion attracted to that chlorine ion, but they don't attract in just like a 1-to-1 ratio, okay? You have the individual ions, and they attract, but they're still there, so they can attract a bunch of other ions, and they get held together in this big structure we call a crystal lattice, okay? So it's all of those ions attracted to all of those other ions in a big organized way, okay? Sodium chloride structure looks like that. As you get into different ratios that aren't just 1-to-1, these crystal structures can get very complicated. But that's what forms the basics of everything, really. Okay? So we need to be able to look at the periodic table and tell who's going to give up electrons and who's going to gain electrons and what ions these things are going to form. Okay, so if you remember, one of the patterns of the periodic table is that elements in the same group or column have the same number of valence electrons. So group 1 here, okay, sodium, potassium, rubidium, cesium, they all have 1 valence electron. Okay, so let's look at lithium, for example. Lithium has 1 valence electron. It's always going to want to lose that valence electron, so it drops down an energy level. So they're always going to form +1 ions. Where group 2, okay, they have 2 valence electrons, like magnesium. Magnesium has 2 valence electrons. That's what its dot diagram looks like. So it's always going to want to lose those 2 and have a +2 charge. The transition metals are weird, that whole middle chunk of the periodic table. So we just skip them. Sorry, hold on a sec. Okay, so we just skip them. They can form different ions based on how their electrons are arranged. For example, another way that we talk about charges referred to as oxidation states. Iron can exist in any of these oxidation states. You can have iron with a 5 charge, a 4 charge, a 3 charge, a 2 charge, a +1, okay? The +2 and +3 are more common, so when we write that charge in parentheses. So if we're talking about Fe2+, okay, we call that iron 2, okay? So that's the rule for basically all metals that aren't in those first 2 columns. Okay. Aluminum has 3 valence electrons. It will form a +3. And then we're getting into that break between the metal half of the periodic table and the non-metal. Okay, carbon with 4 valence electrons, it would either have to lose 4 or gain 4, and honestly, with the way that's arranged, it's just not very likely to happen. Carbon actually very rarely forms an ion. It tends to bond in a covalent compound where they're sharing electrons, and we'll get to those more later. If we look at nitrogen, okay, nitrogen has 5 valence electrons because it is in group 15, so it wants to gain 3, okay, to fill those missing spots. So it always forms a -3 ion. Oxygen, -2, and my halogens, group 17, they will always form a -1 ion, okay, because they're just 1 electron away from achieving that noble gas electron configuration. Noble gases, as we've said before, they have their full outer energy level, so they're already stable, okay? They're not going to form ions. So let's do some examples and we'll get to naming them. Let's look at calcium. Where is calcium on the periodic table? It is right here. It has 2 valence electrons, so it tends to form a +2 ion. Okay, where chlorine, I'm going to use blue for my nonmetals, chlorine is right here on the periodic table. It has 7 valence electrons. It wants to gain 1. So it tends to form a Cl- ion. Okay, now when these things form, they form to balance out the charge, to make it neutral. So we need 2 chlorines, okay? Then we will have a 2 negative charge. Oops, come on. And 2 positive charge. So our chemical formula would be CaCl2. Okay, you can also look at it in terms of their electrons. If I have calcium with 2 valence electrons and chlorine with 7, okay, chlorine's really attractive, so it is going to steal an electron from calcium. Okay, and then if there's another chlorine in the area, which there always will be, okay, it's going to steal another electron. Okay, so now we have calcium with a 2+ charge, and each of these chlorines have a -1. Okay, the number of electrons lost by the metal equals the number of electrons gained by the nonmetal. Okay, so now in order to name the compounds, I have a little flow chart here for you guys. First, you identify the cation. That's always going to be the metal or a polyatomic. Okay, if it's a metal with 1 charge, like magnesium or like calcium, we just name that metal. It is just calcium. And then we identify the anion. That's the non-metal one. Okay, that's chlorine. We change the suffix to IDE, so it's calcium chloride. And if there's a polyatomic in there, we just say the polyatomic. If it's a transition metal that can have more than 1 charge, that's when we use that 2 in Roman numerals. Okay, so let's look at some more examples. Potassium and oxygen. Potassium is right here on the periodic table. So it has a 1 valence electron. It tends to lose that 1 electron and be a K+. Oxygen is right here on the periodic table. It needs 2 more electrons to complete its outer shell, so it forms a -2 ion. So in this one, I have more negative charge than I have positive charge. So I'm going to add in another potassium so that I have 2 positive charge to balance out that 2 negative charge. So the formula is K2O, aka potassium oxide. And you always have to write the metal first. It is not okay to write this as OK. Okay, always KO. Okay, let's look at aluminum. Aluminum is right here on the periodic table. So it forms a +3 ion, okay, because it has 3 valence electrons. Where sulfur is right here on the periodic table. It forms a -2. Now, these ones are the hardest ones to do because there's no way to just add one more of one of these and have the charges balance out, okay? If I add another sulfur, okay, I'm going to need a total of 6 positive and 6 negative charge, aka it's like the least common multiple in math class. But that's the only way to get it, so you have a +6 and a -6, okay, so that those charges are balanced out. So the formula is Al2S3, and we would call it aluminum sulfide. Okay, let's do some ones with polyatomics. So polyatomic ions are ions that are formed from more than one atom. Okay, they're always covalently bonded to each other, but unfortunately, it's something that you just kind of have to memorize. There's no way to know its charge by looking at its formula or anything like that. Okay, barium is in group 2 on the periodic table. So it is a Ba2+. Hydroxide is OH-. Okay, and again, that's something you just have to memorize. You have a table of polyatomic ions. You can find these tables everywhere, but there are 6 key ones that are going to be very important to us in this class that I am, or 8, sorry, that I am requiring you to memorize. Oops, wanted to highlight. Ammonium is the only positive one you need to know. Okay, so you just have to memorize them. No secret here, just be able to see the word hydroxide and know that it's OH-, or see the word phosphate and know that it's PO43-, or sulfate, or nitrate, or carbonate, or chlorite. Okay, cool. Okay, let's go back to our formation. So you'll see here that we have 2 positive charge, but only 1 negative. So we need more negative charge, making our formula Ba. Since we have 2 hydroxides, we're going to put them in parentheses. So it'll just be BaOH2. And we would call it barium. That's not how you spell barium. Barium hydroxide. Okay, let's look at sodium phosphate. Sodium is in group 1. It forms a plus charge. Again, you have to look at the periodic table. Phosphate is PO43-. You just got to memorize it. So we're going to need more positive charge, okay? Because we have 3 negatives, so we need 3 positives. Okay, so our formula then would be Na3PO4. Because there's only 1 phosphate, I don't need to put it in parentheses. But we call it sodium phosphate. Okay. Now, this is an example of one where the charge is given to you. Copper is a transition metal, so it can have more than 1 charge. So that one has a 2 in Roman numerals after it, so we know that it's copper 2+. Okay. Now, chlorine has 7 valence electrons. It wants to gain 1, so it is Cl-. So when they get together, we're going to need 2 chlorines, so it is CuCl2. And we have to call that charge out in its name. It is copper 2 chloride, as opposed to, say we had copper 3 chloride would be copper with a 3 positive charge, chlorine with that 3 minus. So when they get together, it actually bonds to 3 chlorines rather than 2. Okay. And one more example, iron 3, so that's Fe with a 3 positive charge. This is a hard one. And then carbonate. Carbonate is one of our polyatomics. It is CO3, 2 minus. Okay. So in order to balance out these charges, I'm going to need another carbonate. So now I have 4 negative charge, but only 3 positive. So I'm going to need another iron. And another carbonate. That brings it to a total of 6 electrons and 6 electrons, okay? There's a transfer of 6 electrons and the charges are balanced. So the formula for this one would be Fe2. I have more than one carbonate, so I'm going to have to put it in parentheses. CO3, 3, okay? And we would call it iron 3 carbonate. Okay, so again, if you ever see these Roman numerals, that's just the charge on the ion, and that's what you use. Hopefully that was helpful, and you can picture what's going on here. And yeah, okay, cool. Okay, cool.